Good afternoon, everybody. My name is Thiraviam, and I am a simulation specialist here at GoEngineer. Thank you for joining us this lovely Friday afternoon for a presentation on CFD and flow simulation. Hope that isn't very intimidating. Today, we're going to take a look at how we can leverage the traces study tool in flow simulation for contaminant detection. How can we make sure the heating ventilation systems or the rooms that we're in have contaminant levels that are at acceptable levels to foster a healthy environment. Let's get started. What is a tracer study? Now here I have a video of an experiment done by a few students that actually studies flow of water across a cylinder. So you see the red and the blue dye, they're essentially dyes or contaminants introduced in the fluid to essentially visualize how a flow around a cylinder pans out based on the velocity of the fluid. So in the same note, how you can track these contaminants that really don't influence the flow of your carrier fluid, which could be the air that you're in or the water you're swimming in order to study their levels and study the flow paths of the carrier fluid. Now, where this could be really leveraged is in ventilation design, where the carrier fluid is air and you have absolutely no idea how these colorless and odorless gases are about to get you and if they're at dangerously high levels to have physiological effects on your well-being. Moving on, in order to demonstrate this sort of tracer study in action in everyday life, I have set up a garage ventilation problem. So here, the goal is twofold. Essentially, how can we leverage SolidWorks Flow Simulation to study the ventilation system to keep the temperatures at an acceptable level inside the garage? And finally, how can we minimize the carbon monoxide concentration in the garage when we have our car idling? So when you do have your automobiles idling inside the garage and the garage is closed, and if it isn't properly ventilated, the carbon monoxide concentration could get to very dangerous levels that might affect your physiological well-being. Great. Now moving on, the setup. Now as far as the garage problem goes, there are two ventilation systems that I explored, one which is on the garage door and one on the roof or the ceiling of the garage. Besides that, I have two 100-watt light bulbs lined on the ceiling of the garage that act as heat sources, which essentially cause the convection of air by virtue of the heat transfer between the light sources and the air inside. Besides, you cannot have a perfectly closed system. There's usually a little leakage between the garage door and the garage itself. So I've essentially, modeled out two holes by which, air can either get into the system or air can get out of the system based on the convection that takes place on the inside. Great. Now, I essentially studied three cases for garage ventilation. One system with absolutely no vents, the other system with just the roof vent active, and another system where just the door vents are active. Essentially, the goal of this analysis is um, displayed in the schematic. Now, we have air leaks through the walls. The garage is at a negative pressure. Now, how can we evacuate the hot air that's inside the garage through an efficient ventilation system? Now let's jump into SolidWorks to see how such a problem is set up with flow simulation. Now here's my assembly with my car parked inside the garage. Um, Now to start off a flow simulation analysis, all you need to do is get into the SolidWorks add-in tab and grab the SolidWorks flow simulation button. Once the flow simulation solver is added into the CAD interface, all you need to do is jump into the flow simulation tab on the command manager to set up your problems. Now CFD can be a little intimidating to set up, so what the uh, developers at Flow Simulation SolidWorks have done is essentially coupled everything that you need to set up an analysis into one fluid interface. Now, uh, how this interface can be accessed is through this button called the wizard tool. So anytime you start off an analysis, you essentially use the wizard tool to tell the solver what kind of analysis you're solving, what are the fluids in your analysis, and if there are any adverse heat transfer effects in your analysis. And there's one thing I missed out. So prior to starting the problem, so essentially you'd like to understand only what's happening inside the system and you don't really care about what's happening in your environment. Typically, this is what we call an internal analysis. And prior to starting off any internal analysis, it's good to see if you have a closed watertight volume. Now, in flow simulation, we have a check geometry tool that you can use in order to check if you have a closed watertight volume. Once this solver picks up a fluid volume, it indicates it successfully captured a domain inside your system. Now, if you want to see what this domain looks like, you can hit the Show Fluid button. That indicates the fluid domain where the analysis is going to be run. Great. Now that you've validated that you have a closed watertight geometry, now let's set up this internal analysis. Now, grabbing the wizard tool, the first page, if you will, is essentially inputting the project name. I'm just going to call this project setup. Now, you can select configurations on the fly using this little configuration button. Now, I'm just going to use my default configuration for the analysis, and I'm going to hit next. Now, depending on the design parlance that your company is accustomed to, you can pick unit systems that are predefined, or customize your unit system based on what you're accustomed to, speaking with your designers on a daily basis. Now, once you have your unit system defined, you go into the analysis type page. This is essentially the meat and potatoes of the flow simulation package. Or the flow simulation solver. You essentially tell the solver what kind of analysis you want to run and what additional thermodynamic or radiation or convection effects you want to add to the solution. So right now we are setting up an internal analysis. So let's just leave it at internal. Now gravity, essentially hot air rises, cold air falls by virtue of density change with temperature, and essentially setting the direction of gravity sets the direction of your fluid motion in your system. So this becomes an essential aspect of convective heat transfer. Now for our analysis, we wouldn't need the heat conduction salts, like I said. Now it is an internal analysis, and where convective heat transfer is the most prominent form of heat transfer. So let's just set the direction of gravity and hit next. Now in the default fluid page, it's pretty self-explanatory. You get to pick from the engineering database what fluid essentially fills up this entire system. So this time the fluid is going to be air. Now once you've picked your fluid, you can go on to the next page. Now if you'd like to set a thermal condition that might influence how heat is transferred between the solid walls and the fluid inside your system, this is where you set it. But right now, since we're not really worried about conduction, let's assume that all the walls are insulators or adiabatic. Now, this is essentially sets up the initial condition of your system. Now, the closer this is to the final answer, the faster your results. But an intuitive way of thinking about it is, hey, what is the starting point of your system? Is it at 20 degrees? Is it at 10,000 feet over sea level, or is it at sea level? Now, here, let's set the starting point of the system at 35 degrees. Well, it is a hot day. Now, this essentially dictates how the computational domain is broken down into smaller elements. The smaller the elements, of course, the more accurate your results and the longer your computation time. So with flow simulation, you can use a slider in order to pick how refined you'd like to make all the elements in your computational domain, and control the accuracy of your analysis. Now, you push the slider over 5. This sets up something called a solution adaptive refinement algorithm that essentially refines your computational domain or your analysis as the flow simulation solver is actually crunching out the math in the background. Now, in case it does find areas that it does not have enough elements, flow simulation has the ability to automatically add and populate enough elements in those areas in order to continue the computation. Now, as soon as you set this up, the first thing that happens is you have this little project manager for flow simulation that populates all the projects you've set up. And the second thing that happens is you have the analysis tree that essentially lets you set up an internal or an external analysis. Now, the first thing you want to add here is essentially boundary conditions. Now, since you have 2 leaks at the front of the garage, that'll be the first area where we specify a boundary condition. Now, just grabbing the inside faces of the leaks and setting up an environment pressure condition essentially exposes that to the environment. In the same way, the next set of boundaries will be for your vents. So I'm just going to set up a flow rate at the vents over the garage door, that is. So I'm going to grab the insert boundary condition tool, grab both the surfaces corresponding on the side of the computational domain, specify a flow rate, and that's my internal analysis problem. So I'm going to grab these two split surfaces that are representative lights and add surface heat sources. So I'm going to add a 200 watts. That's essentially going to influence the quality of fluid flow in your system. And once I've set these boundary conditions and the heat source and the heat sources in my computational domain, I'm ready to run the analysis. Now I'm going to jump to a system that I've already created, or a project that I've already created. So for my first analysis, all I did was set up these leaks and use the car and the ceiling lamps as heat sources. Now with flow simulation, you have the ability to track temperatures, pressures, and flow rates at different parts of your system by selecting uh, by selecting faces and assigning a specific parameter that you'd like to analyze on that surface. I'm going to track the surface temperatures of these two areas, and I'm going to use that as my temperature criteria to justify the efficacy of my ventilation system. So after I've run the analysis, this is what the flow trajectory looks like by virtue of the heat sources. You can essentially see air circulation at the leaks, where air enters at the top portion of the leak and exits at the top portion of the leak and enters the garage at the bottom portion. Great. Next, I'm just going to activate the temperature plot. Now this indicates that my temperature distribution is between 40 and 45 degrees, indicating a really hot garage. What I can do with flow simulations, once I've set up multiple projects, I can compare the temperature plots or any sort of output between, across various projects. So here you can see with my roof vent on, uh, the temperature in my garage is much lower. So as soon as I grab the compare tool, I grab the cut plot that I'd like to compare and all the projects that I'd like to run the comparison against. I can essentially see the thermal performance of my system for different projects. Okay, great. Now running back to my presentation, now when with the sensors that we've set up, this is essentially the thermal performance of each system. So with no vent, you have a really high temperature of close to 88 degrees, which is sort of alleviated by in the roof vent and the door vents. But what about contaminants? Now, essentially, there are catalytic converters and emission controls that are placed in your system, in your vehicle emission system, that oxidize all the harmful gases that get into the environment. But there are certain cases where, due to incomplete combustion or other effects, that you could get carbon monoxide emissions or nitrous oxide emissions. Now let's try using the tracer study tool to essentially check carbon monoxide emissions. What volume of carbon monoxide actually fills up your system, and if it actually at a dangerous threshold to affect your physical well-being. Now let's do a little contaminants 101 here. The chart on the right essentially indicates the concentration level of carbon monoxide and the effects it has on human health. So essentially we'd like to be somewhere between normal fresh air and possible health effects with long-term exposure. So that's 0 to 10 ppm. So ppm is fancy talk for parts per million. It's essentially the number of parts of your contaminant uh, to a million parts of your carrier fluid. In volume fraction terms, this translates to 1 e to the negative 6. So in our analysis, we need to make sure our volume fractions do not exceed 10 ppm and is always between 2 and 10 ppm. Now, how do you set up a tracer study? Now, the tracer study is a post-processing tool. All you need to do is to set up the tracer study is, I'm going to hide my temperature plot. I'm going to grab the tracer study item, hit the wizard button, and essentially make assignments in each page of the wizard. So I'm assigning a name to my tracer study. Next, I get to pick from my engineering database the different tracers I have in my system. Now, since I'm using carbon monoxide as the contaminant, I'm going to pick that up. Now we're not going to have this as a time-dependent analysis. We're going to only have this as a steady state. You essentially want to see what the steady state concentration, carbon monoxide concentration in your system is. Now this is the initial condition of the system, which is meaningless without any time-dependent effects. Now this becomes essential, so you have to pick the source for the tracer. So I'm essentially, the outlet of the exhaust pipe is your source. Once I grab the outlet, I'm going to specify a flow rate for the tracer. Here the flow rate that I'm specifying the tracer is about 1 e to the negative 6 kilograms per second. Now once I have that set up, all I need to do is hit run. Okay, great. Now once the tracer study is complete and the tracer is active, what I can do is I can activate cut plots that essentially tell me the tracer mass fraction in my system. Now I'm going to reset the curves to read 2 ppm to 10 ppm. So you can see with the in the roof vent on configuration, the tracer amount in your system is at a level lower than 2 ppm, indicated by the blue in your system. There are only certain areas that are close to the exhaust pipe that essentially have a large amount of carbon monoxide concentration. In the same way, in running this analysis across for different configurations, you kind of tend to see the good, the bad, the ugly of the carbon monoxide concentration. So with the door vent and the roof vent configurations, you do tend to keep the tracers between 10 and 2 ppm, but with the no vent configuration, the tracers exceed 10 ppm. Now just going back to the analysis, activating the vent off configuration where the garage is invented, activating the tracer study, to look at the tracer amount. So this indicates essentially that a majority of the carbon monoxide concentration is in the 100 ppm level, or is between the 30 to 100 ppm level. Okay, through this exercise we've kind of studied the steady state configuration of your system. Now essentially, how long does the concentration take to build in the system? Now by virtue of the flow rate in the system, now if I'm running the system for about 10 minutes, how can I essentially say trace the path of a specific concentration in my system? Now of course the tracer study tool supports a transient analysis, which you can run on the fly after you've studied your after you've run the actual flow simulation study. So I'm going to run the transient tracer study for the forward vent configuration. Now again, to run a new tracer study, all I need to do is right click tracer study, hit new, grab the tracer that I want to fill up my system, grab the time dependent option. Now as soon as I grab the time dependent option, I get to pick how long I'd like to study the system for. So let's study the system for about 10 minutes, and let's set the time step for the study to about a minute. Now the lower the time step, of course, the more information you're going to get with respect to the tracer distribution in time, and the more accurate that information is going to be. Now besides setting the time step for solution, now you get to set the time step for saving your results as well. That saves plenty of memory if you are actually running this analysis for a substantial amount of time. So right now I've set the analysis to run for 10 minutes, set the step size for the calculation at 60 seconds, which is every minute, and set the saving result step at the period of saving to a minute as well, starting at the 0th second. Now once I have that set up, all I need to do is set up a surface source, which is similar to the previous steady state step. Again, grabbing the inside face of the exhaust and specifying a flow rate of 1e negative 6 kilograms per second. Now I'm going to jump to a tracer study that I've already run. Now, as soon as I activate the tracer study, my results update in order to actually display the tracer study under study. So I can set up multiple tracer study with different fluids and just activate different tracer studies in order to study the concentration or the mass concentration of the respective gases in each study. Now, an ISO surface is a great way of plotting the concentration of your tracer, a specific concentration of your tracer, and where it occurs in your volume. So this essentially indicates at the at the 10th minute how the tracer has distributed throughout your system. But if you'd like to see where it started and how it actually progressed to this stage, you can leave the ISO surfaces active and essentially load time moments in your tracer study. So right-clicking the tracer study corresponding to the transient tracer analysis, you can hit load time moment. And let's pick what happens at the first minute. So at the first minute, the tracer shoots to the ceiling. Now let's see what happens at the 4th minute. And there you have it, the 8th minute. And finally, the 10th minute. So you can quickly see how what insights you can gain out of setting up these tracer studies in order to maintain the concentration of a harmful gas at a minimum and essentially study the distribution of this contaminant with time. Now, jumping back to the analysis, the tools we essentially leverage today to make these inferences about carbon monoxide contents in our system is the following. So, flow simulation is essentially a general purpose CFD solver that has modules that are added in that essentially cater to specific industries. Well, the electronic cooling module caters to the electronic cooling industry, the HVAC module caters to the heating, ventilation, and air conditioning industry. Now, we essentially just used the tracer study in order to make inferences in our analysis. But besides the tracer, we do have a couple of other interesting features in the HVAC that warrant some attention. Starting off with an extended engineering database. So typically, when you set up these sort of heating and ventilation analysis, you'd like bulk thermal properties for your building materials. Now, you can either go look for these building materials from manuals or manufacturers, or you can use the extended engineering database and simulation and use the thermal properties that are built into the database. Besides, the advanced radiation capability enables you to specify absorptive materials. So glass has a tendency to reflect certain wavelengths of radiation and absorb certain wavelengths of radiation. So you get to specify the range or pick out of a material database for different kinds of glasses what's the absorptive characteristic or the wavelength dependent characteristics for radiation absorption in glass. Now, besides this, thermal comfort parameters are another important is other information that people from the HVAC industry are interested in. Now, here what I have is a predicted mean vote. So the closer this number is to 0, the more comfortable your environment. The further away it is from 0, the hotter or colder your system is. That concludes my presentation. Essentially, to sum this up, we looked at how we can set up a basic internal analysis to study the ventilation system in a garage, and we use the HVAC add-in to use the tracer study tool to look at the contaminant dispersion in our system. Anyway, my name is Thiraviam, and thank you for sitting in.